And then there is also the trace of this scattering matrix at 1/2. Okay, so this is not the approach that Anna presented yesterday. It's somehow equivalent, but for some reasons in our work, we prefer to use the Seeberg zeta function instead of going through spectral zeta functions. But it turns out that in some intermediate steps of the proof of the theorem, these kind of functions arise and could also be used as a replacement. So then you can show meromorphic continuation and holomorphic at z equals 0, and then you define a regularized determinant of hyperbolic Laplacian as in the smooth case. And the equivalent metric on the determinant of the cohomology of the trivial sheaf. So I recall you that this is only for the trivial sheaf, because here we can use spectral methods as before. Will be defined as the typical rescaling of the L2 metric that I discussed yesterday, which is well defined. And this, let me just insist that since I didn't use the right normalization for the Laplacian, this in the compact case where everything is really defined classically and as used in the work of Gilles-Soulet, this is not coinciding with their equivalent metric underlying to our metric datum, only up to a constant, but I don't want to discuss the constant. So remark in the, say, compact case, since we didn't pay attention to normalizations, so this is only the usual equivalent metric up to constant, but the constant is explicit, so metric up to constant, it is explicit and depends essentially on the genus of the Riemann surface. Okay, and now with this you can define the equivalent metric, and I will just recall the statement of the theorem that I gave, and that was also recalled by Anna. So with this, we have the theorem that for an arithmetic surface coming with some sections corresponding to cusps and elliptic fixed points, this is a set of, has to be thought as a set of cusps or elliptic fixed points. So I imagine that on the complex points, this Riemann surface can be uniformized as a quotient or a bunch of quotients or completed quotients like this. And these cusps will have some elliptic fixed points, will have some multiplicities. For cusps is infinity. So then we have the formula that 12 times the arithmetic degree of the determinant of cohomology of the trivial sheaf with the equivalent metric, plus this combination of log p's that measures that reduction, plus the contribution concentrated at the points where the singularities happen, where we use some renormalization of the hyperbolic metric called the Wolper metric. This is going to be the arithmetic self-intersection number of the relative dualizing, twisted by the sections with suitable multiplicities and with the hyperbolic metric. And this will be up to an explicit constant whose shape we saw yesterday in the talk by Anna, depending only on the type of the function groups involved in the uniformization. So namely the genus, the number of cusps, the elliptic fixed points, and their multiplicities. Depends only on these things. And involves this funny log derivative of zeta at -1 and things like that. OK. So I would like to discuss the next step, 2 applications of this formula. Applications. So I announced what is the plan for the rest of the lectures. So I will apply, well, just before that, some remark. So this suppose the choice of a regular model, if you want, of a curve of defined over k. And so you get an equality of real numbers. And for the sake of simplicity, so to simplify the forthcoming steps, I will not work with the integral model. So I will just work with the curve defined over a number field, which will be Q. And this has the effect that instead of getting an equality of real numbers, you get an equality of real numbers up to some log p's. This is because I just don't want to discuss too much about some facts about Jacobians and their models and their heights and et cetera, et cetera. So I will use this. So the idea is that if you just want to resolve for a curve over a number field, you can apply this theorem to any model, regular model for it over spec OK, and then you get an equality of real numbers that depends on the choice of model. And this choice of model, if you want to remove this ambiguity on the choice of model, you have to mod out by the ambiguity in each choice, which is given by sublog p's and whatever. So, but this is just quite formal. You will see that the application is quite formal. So, so version of the theorem for x defined over a number field, but with values in R mod the Q vector space spanned by log p. So I write it this way. Of course, then the interest depends on how transcendental the quantity are, because it could be that when you do this transformation, you get 0 equals 0, and you are not even aware of that. So, but sometimes assuming some conjecture on periods, you can expect that this is not going to be a trivial equality. Okay, the application that I have in mind is the following. Apply the theorem to a modular curve, and in our case will be a modular curve of the form x depending on some level of the type gamma 1n intersect with gamma 0d, this shape. So this will give spectral or automorphic, this can be seen as an automorphic expression for the right-hand side of the formula for the self-intersection of omega x, let me call this x over q of these things. So I will be a bit lazy, and actually if I put the gamma 1 structure is in order to avoid elliptic fixed points, so actually this will only be cusps. But in principle, what I'm going to do can be done even with elliptic fixed points. So, and this kind of numbers, so we already saw in several lectures what is their shape, that they can be computed in the case of modular curves, can be computed thanks to the Kroenecker limit formula. And the fact that you can talk about Kroenecker limit formula has a lot to do with the existence of cusps. So I'm not interested in the computation of this number in this talk. So then you can apply also the theorem to a Shimura curve. Which it will be a compact analog of this modular curve. So the Shimura curve, let me call it y, which is a compact. You also have some levels, and it will be attached to a quaternion algebra. The details will come later. So this will be a compact Shimura curve. And you have the same interpretation of self-intersection number by Riemann-Roch again. And this is the Riemann-Roch of G.Freixas in this case. So this will give a similar automorphic interpretation. So the automorphic part, of course, comes from the cohomology with equivalent metric. So similar automorphic interpretation for some self-intersection number like this. And if you know a little bit the literature, so and you know this computation of this number by Boston-Kuhn. And you know the computation of this number by Kudler-Rappaport-Young. Compute it. This is which have the disadvantage that they don't have, which seems sometimes life. You know that these two numbers up to some log piece that will actually depend on the arithmetic or of the somehow the bad reduction of either the modular curve or the Shimura curve. These two numbers look very much similar. So these two numbers are very similar. And as Chingy said in his talk, they are given in terms of zeta prime of -1 over zeta of -1. So I'm actually interested in this kind of numbers, the transcendental aspect, if you want, of the numbers. So and well, it's not very surprising. Now we are quite used in the to this kind of computations, and we know that the Shimura curve is not that different from a modular curve, but still, I mean, in each case, you have to compute, you have to develop your techniques, et cetera, and you may wonder why this happens from an abstract point of view. And the reason is that So Riemann-Roch, or the reason I propose is that the Riemann-Roch Fourier transforms these things in automorphic information, this thing and this thing there, and that in terms of groups, these automorphic forms on one side for GL2 over Q, and on the other side, the Shimura curve side, they correspond to an inner form of GL2 of Q. And when the groups are so similar, you have this Jacquet-Langlands correspondence that establishes a bijection with some properties between the automorphic representations for one group and the other group. And so it gives some relation between modular forms, classical modular forms or quaternary forms, which is usually used. And also gives the same thing for non-holomorphic modular forms. It's a general thing, doesn't care about being holomorphic or realistic. So, and these are all the ingredients that go into Riemann-Roch. So actually, the Jacquet-Langlands correspondence will say that there is a relation between the cohomological sides of Riemann-Roch, and then this gives the relation between numbers. And this is something I will explain here for this geometric situation. Also works on other contexts, and this was mentioned by Chingy too. So for twisted Hilbert modular surfaces and some complex Shimura curve, this can also be done, but it involves high dimensional version of arithmetic. This I didn't present, so I will stick to this situation. So now the aim is just to recall a little bit some preliminary and classical facts about modular curves. So yeah, after a week of seeing general Shimura varieties, this will look like a toy, but I need some facts that I prefer to recall. So just recall. How modular curves arise. So on from the complex point of view, on the one hand I have the upper half plane. And I know that any torus of dimension, complex dimension 1, can be written in terms of uniform height by C, mod out by a lattice isomorphic to some Z plus Z tau. So I have an arrow that goes from H to elliptic curve that sends tau to something like this. So any elliptic curve is isomorphic to something like this. And if you insist to view modular curves as given by such quotients, isomorphism classes of elliptic curves, so correspond to the action of PSL2 of Z here. So if you look at isomorphism classes here, then this corresponds to the action of PSL2 of Z. And if you take classes under these equivalencies, so you say that this quotient corresponds to elliptic curves modulo isomorphism. So every is sent to the isomorphism class of this thing. So this has the structure of a Riemann surface, and the typical way of saying this is by writing the J invariant of elliptic curves that establishes a bijection with complex numbers and provides the structure of Riemann surface here. And as we saw, this can be compactified by adding a cusp. So by adding the point at infinity, which is called cusp, and on the level of the upper half plane, this corresponds to adding the rational points of the projective line, real projective line, seen as the boundary of the upper half plane, and with the other presentation through the J invariant, this is just adding the point at infinity, so of a P1. And the neighborhood here of infinity has coordinate Q equal to exponential of 2 pi I tau. And if you want to understand the shape of the elliptic curve, parameterize instead of coordinate tau to coordinate Q. So this corresponds to elliptic curve presented in this way. So you see somehow that when the parameter Q approaches 0, this family of curves will approach to a torus. And this is the kind of generalized elliptic curve. When Q converges to 0, then this family degenerates to C star as an algebraic group. And an equivalent way of seeing this is like compactifying C star. So you take P1, you identify 0 and infinity. And so when you remove this singular point, you get a C star. But I say that this comes with the structure of algebraic groups. So actually here I have this distinguished point, which is 1, and which will be the neutral element of the group structure of C star deprived of the singular point. So this kind of objects, so with the algebraic group structure, when deprived of the point where we made the identification. So this is a very particular example of generalized elliptic curve. And this is the notion that you use to properly define compactifications of modular curves with some higher level. So and it's not really that point of view that I will use, but I wanted to recall this. So this is an example. Of generalized elliptic curve. And this picture can be extended to higher levels, like gamma 1n or gamma naught, and is used by the linear Rappaport to provide compactifications and integral models, to provide compactifications with a modular interpretation. So plus, so an integral structure. And this also allows to study the regularity of the models that you will obtain. So when I say integral structures, I mean models. The regularity or normality or whichever condition you can prove. And also, well, other approaches are given by Katz-Maser. Where they actually only provide integral models of open modular curves, and then they use some normalization. Oh, this is well, there is a mixture of both. I never remember which one it is, but they can be married. So they are part of a single approach, and this is very nice explained in the paper. By Brian Conrad, and he also discusses these objects from the point of view of stacks, and he discusses very nicely whether you have the map for stacks, art in the stacks, etc. So these are nice references that are a natural place where to start studying compactifications and models of moduli spaces of elliptic curves, and then in higher dimensions it becomes much more complicated, and you don't have such a nice moduli interpretation of compactifications. There are usually choices involved, not always, but quite often. Okay, I would like to discuss more in detail the case of gamma 1 of n. We discuss gamma 1 of n. So this, the quotient you can easily see that this quotient corresponds to an elliptic curve with a point of order n. So couple given by an elliptic curve and an n torsion point of order n. The boundary has also an interpretation as in terms of generalizations of the one gun, so the P1, the nodal curve I pictured. And I'm not going to make this interpretation for lack of time, so I will just say it by words. So Cas correspond to some d dividing n gounds of P1s with a group structure when deprived of the vertices. So things like this. And then P will be a point of order n whose, say, orbit intersects all the components of order t, sorry. And P, actually, from P you will get a positive divisor. When restricted to all components. So this can be formulated, as you see, I mean, not very precise, but these things can be formulated in a schematic way. And this is what you need to do to define models. So this can be translated into the schematic language. But I will just do it for the easy part. So for instance, away from Cas, so not Caspidal curves, you have families of elliptic curves over a scheme S. So this means proper smooth with geometric connected fibers with a group scheme structure. And P in this case, so En is what is called a finite flat subgroup. And the point P will correspond to a section. It's a section of exact order n for the additive structure of the curve. Okay, so this the functor classifying subject objects will provide a model of the modular curve. The functor these objects has the structure of a scheme if say n is bigger than 5, and actually, I mean, including the compactification that I didn't define, and actually what you can get, for instance, with this is a proper smooth scheme like this. And what primes dividing n is a little bit more subtle, so I don't want to discuss this. Proper smooth integral, etc. So to obtain the best version of the application that I want to give, you should use these things. But here I will just consider this over Q. And what I will use is that the locus parametrizing a generalized elliptic curve defines a cusp, defines a relative Cartier divisor, which becomes rational if you add the nth roots of unity. So the locus parametrizing, I will say it this way, they generate generalized elliptic curve is a relative Cartier divisor. That becomes rational, so given by sections if you want. Over, so you have to add the nth roots of unity. I will be interested in the cusp at infinity and this one rational. Very well. So a slight variant is what I will denote by x1, but with 2 entries. So n and m will be co-prime, and n will always be bigger than 5. And this will correspond, at least over the complex points, to the to the compactification of these quotients, and this parameterizes so generalized elliptic curve, actually, but let me say just the open part. Generalized elliptic curve vibration together with n torsion point and a cyclic subgroup of order exact order m. P n torsion point, and C is going to be a finite flat cyclic subgroup of exact order M. And this is needed to define Heck correspondences. So these are our objects. Okay. Okay, so for later use, precisely because Jacquet-Langlands correspondence in question has to do with automorphic forms. Automorphic forms have to do with modular forms or analytic or holomorphic, which are proper under the action of this algebra of Heck correspondences. I will now use these objects to define the Heck correspondences. And diamond. Morphisms. So I start by the Heck correspondences. The Routh picture goes as follows. So n bigger than 5. I look at these things. I could also look at mixed things, but I will work with x1n for the time being. And I take m coprime with n. And the Heck correspondences arise from two basic relations that you can have between this curve that classifies elliptic curve with n torsion points and these mixed objects. So any elliptic curve with a torsion p point can be enriched with a cyclic subgroup of order n in several ways. And you have another relation that links this mixed object with the base modular curve, is that if you have a modular curve with a point of order n and a cyclic subgroup of order m, you can divide by the action of this cyclic subgroup to obtain a modular curve, an elliptic curve only with a torsion n point. So this is where this hypothesis is in. And this gives a correspondence. This is the correspondence. Given by the following arrows. So you take an elliptic curve over a base S. You take a point of order n, and then you take a cyclic group of order m, and you can do two things. You can forget the group, or you can mod out by the group. I don't write the basis scheme anymore. So you take P mod C, and then you don't have the group anymore. So this gives a correspondence. It's a finite correspondence. And the advantage of having this modular interpretation is that you see right away that this correspondence works over Q, for instance. And this acts as any correspondence. So I will write this correspondence Tm. This is the notation, and acts by functoriality. There are several ways of seeing saying this, but I will say that it acts by functoriality on the Jacobian of this curve. So, and hence, on dH1 of J0, sorry, on the invariance differentials. And now I have to put the base. So in this vector, so as I said, I will be mostly interested to working over Q. But actually, as I define it, I could at least easily work here. Well, we should be careful with them. So in the invariant differentials of the Jacobian are canonically isomorphic to the global differential forms on the modular curve. So this gives the action of the Hecker correspondences here, and this will use later as the space of cast forms, actually, but I don't need it right away. So, and this is written again Tm. And I will probably finish calling the diamond operators, which are similar, well, they also act on differential forms, diamond operators. So for any, say, integer coprime to m, you can use multiplication. So, so here we are classifying curves with n torsion point. So I can use multiplication by d to produce, well, to another torsion point. And so this gives a morphism of modular curves, and these are called diamond operators. So this goes from at least for elliptic curves, it sends EP to E d times, and it will also act by functoriality on this space. By functoriality. Acts again on the global differential forms on the modular curves. And the last remark to finish the talk is that tomorrow we'll use that this is the same thing as the space of cast forms with rational Fourier coefficients at infinity. And these correspondences can be written in terms of Q expansions by the classical formulas. So actually, th0 is the space of cast forms of weight 2, and the action of the Tm and the diamond operators can be given by classical formulas on Q expansions, Fourier expansions. And I'm personally unable to remember the formulas. So this is just a geometric version of this. Oh, and another thing is that, of course, these operators Tm and D together form an algebra, which is called the Heck algebra. So we have some room here, and I finish with this. Tm and D span an algebra contain, if you want, in the algebra of endomorphisms of the Jacobian, called of finite type. It's free of finite type over Z, which is free, and is called the Hecke algebra. Algebra here. So we'll use this tomorrow. So I stop here.